Can you hear me? Hello? Can you hear me?
Yes, sir.
Okay, let me start. Look, in the previous note, I have one left, Dini's theorem, but I want to talk about Ascoli-Argiolet theorem. That is, I think, note 23, I think, that the printed note, Ascoli-Argiolet theorem. Okay, that I want to talk about. In order to talk about Ascoli-Argiolet theorem, again, I am repeating here that equicontinuous function. So, suppose X tau is a topological space and you have a non-empty collection of continuous functions, real valued continuous functions on X. Cx is the collection of all real valued continuous functions on X. So take this thing. We say that A is equicontinuous at A if given epsilon greater than 0, there exists a neighborhood. Look, it is essentially the definition of continuity of a real valued function at a point. But here, this neighborhood I get, it works for all f. This is important. This is but the same as definition of continuity for one function. Basically, you are doing for all functions in A. That is important. So that is equicontinuous at A. Okay, and if it is equicontinuous at each point, okay, then we say that it is equicontinuous on X. Okay. So in that note, which I uploaded last night, Ascoli-Argiolet theorem, first definition, let X be a topological space and S be a non-empty subset of, instead of here A, I took S. S is a subset of Cx. Okay. Then look here, the given epsilon greater than 0, choose a point here. That the common, that point, instead of A, I am doing it X here. So there exists a given epsilon greater than 0. There exists a neighborhood V of X in X such that you have this Fy minus Fx less than epsilon. First of all, for one function, this is for all y belongs to V, and this is true for all this. Okay, for all and for all f belongs to this. This is important. If S is finite, then automatically it will be continuous, because that I told you that you will get for each point. Suppose S is only this. So suppose for F1 you get the interval V1 at a point X, and similarly for Vn. Then if you take V equal to this, then it will work. V will work. So that actually when you give the definition, it becomes important when S is infinite. For finite, it will be always equicontinuous. This is infinite subset of Cx. Okay, X is called equicontinuous, then S is called equicontinuous. This definition. Equicontinuous at X. This is one point at X you are defining, and if it happens to be all points, okay, if it happens to be continuous at all points, hello, क्या problem है? I don't know what happened. Suppose now S is equicontinuous if S is equicontinuous at each point of topological space X, then S is called equicontinuous. Equi, that is same neighborhood is working. Given a point, same neighborhood was working. Okay, right? Here, now look, if you take X is a now definition point-wise bounded. S is called point-wise bounded. This is an important concept, particularly in function analysis. Point-wise bounded. I defined. It means at each point the collection. Look, this is a collection of functions. Again, if it is finite, everything will be automatically satisfied. So it makes sense. Basically, becomes important when this is infinite. Point-wise bounded. That means if you have this for each x, first you take x, any x belongs to x. Then you take this thing, fx. X you are not changing, the f belongs to s. Look, this will be a subset of R. Okay, this may be bounded, may be unbounded. If it is a bounded function, then obviously it will be bounded. But okay, now suppose it is bounded. So suppose given x, this. So this is the thing you are taking. Okay, so you call it, you can call it SF. Suppose given x belongs to x, there exists a max. It will depend on x greater than 0 such that SF, look, fx, such that fx less than equal to mx for all f belongs to s. This collection, so this will x will depend, the mx will depend on obviously on x. We say actually that we do not use. We say that S is pointwise bounded at x. S is okay. This is now suppose it happens for each x. If it happens for each x, then we say that S is pointwise bounded. Then we don't need it. If that means if S is pointwise bounded at each x belongs to x, then S is called pointwise bounded. Look, this is not something you did boundedness in a metric space that we'll talk about now. This is pointwise. This is basically you need a functions, collection of functions. You have a collection of functions from x to r. Actually, I don't need for continuous functions because for this definition. Okay. But since I want to do it, Ascoli-Arjela theorem, I need Cx. Now, look, we have done it. If x is compact, that's the third part of the definition. Then we have seen that if you have this continuous, then f is bounded. Every function will be bounded, so that when x is compact, I have Cx is the last time I talked. Cx is same as Cbx. Cbx means which is continuous as well as bounded. Okay. So that means it's a subset of Bx. But on Bx we have this big metric D, which is called supremum metric or uniform metric. So that on this you have, if X is compact, then I have this metric space. Look, this is called, because we give uniform convergence, so it is called supremum metric or uniform metric. Okay, or uniform metric. Now look, if you have this, so look at this, that X compact and you are looking for this metric space. So any metric space we have the concept of boundedness with respect to this metric. This is not pointwise bounded, previously I defined boundedness. Now look here, it will, you can easily check, this will be bounded. Suppose S is a subset of Cx, then you can easily check S is bounded in, you should check, bounded in Cxd because I can have a reference function. I can look at the functions. Look, I can have this df0, which is sup of fx minus 0, 0x0, x belongs to x. That means sup of fx. So that is actually will give you the boundedness. Okay. So this is bounded if and only if it is bounded with respect to that I mentioned before. If you take the reference point, this is the constant function 0. Constant function 0. If and only if there exists m greater than 0, it won't depend on m, such that this sup of fx, x belongs to x, less than equal to m for all f belongs to x. S is bounded in this thing. Okay, this actually we have a notation because this metric D is also use it like this. Okay, in function analysis is a common notation, so that this will happen. That means S is bounded in Cxd if and only if you have this. In this case, S is also called uniformly bounded because this uniform metric, it is bounded with respect to the uniform metric. So S is also called uniformly bounded. Look, here is the reason of why it is also called uniformly bounded. Look, here when you have one function that is bounded because it's a compact metric space I have taken, but that means there will exist mx greater mf greater than 0 such that you have this. Sorry, I can write this fx less than equal to mf for all x belongs to x, because f is a bounded function, x is compact, so this will get, but that will depend on f. But here look what I am getting, this is not depending on f for, oh sorry, I've written here for all f belongs to s, but here For all f, same number m is working. It doesn't depend on f. That is the difference. Look, the sup of fx. This means fx mod fx less than equal to m for all f belongs to x, for all x belongs to x. Okay, so that same bound is working. That is why another reason why it is called uniformly bounded. Okay, uniformly bounded means actually bounded with respect to this and means this. Okay, same, but this means actually, look, you can easily check that from the definition it follows if S is uniformly bounded implies S is pointwise bounded. Just use the definition. S is uniformly bounded means S is pointwise bounded. Okay, right? But this need not be true. Okay, right? Now, remark 1.1, you don't need to worry about it because I have not explained that. But actually, C row X, suppose X row is a metric space. Row is the usual. Suppose here you have taken R row is R. Suppose X is a, look, 0x, let me define. What will be 0x? 0x is actually this. Row is the usual metric on this. Okay. Actually, I have taken this. I am taking Cx, same as what is saying 0x. Okay. I think this is from the book. You may ignore this thing. Okay, this I need unnecessarily need to explain a lot of things on that. I don't need this. Okay. Right. So that forget about the remark 1.2. But before explaining theorem 2.1.2, look. Before that, look. Here is saying that you take, this is Ascoli-Arjola theorem. Let me first explain that. This is the Hind model analog, but apparently you are not saying I have given something JAL. It is not compactness, but that as a corollary. So the original Ascoli-Arjola theorem comes as a corollary to this. Look here, what I'm saying. Here your hypothesis. Hypothesis is first X is a compact Hausdorff space. So in particular, you can take a metric space, compact Hausdorff space. So that you can have this thing. Txt is a metric space. This is uniform metric. Now suppose you have this as a non-empty subset of this Cx. Then I'm saying following are equivalent. What I'm giving. I'm not talking about compactness, but that is very simple. That I will explain that. S is totally bounded. Look, in a metric space, you have the concept of totally boundedness. Totally bounded in this metric space. Basically, we are comparing different type of boundedness. Totally boundedness, I have explained pointwise bounded, uniformly bounded. That I'm saying. But here B is totally bounded, S is uniformly bounded. That means actually bounded, uniformly bounded means bounded here. And this is totally bounded, stronger condition. Uniformly bounded in CXT. एक मिनट होल्ड करो. हेलो, सिंह जी बोल रहा है. सिंह जी, आपका स्टूडियो अभी खुला है ना बंद है? कब खुलेगा? हाँ, वो एक्चुअली मेरी बेटी के ना सीबीएसई एग्जाम के लिए वो क्लास 12 के लिए ना एक फॉर्म भरना है, उसका एक फोटो चाहिए. वो फोटो में नाम चाहिए, डेट भी चाहिए. 2 साल पहले मैंने क्लास 10 एग्जाम के लिए आपको लिया था उधर. अच्छा ठीक है, आप कर देंगे तो बहुत बढ़िया होगा। ठीक है, थैंक यू। Sorry for this. This is uniformly bounded means bounded here. And here I am taking the stronger condition, totally bounded. So totally bounded will mean this, but B may not imply A. That's why I need plus S is equicontinuous. That is the concept is coming, equicontinuous. And when you have the equicontinuous, uniformly bounded is stronger than pointwise bounded. Look, totally bounded is stronger than uniformly bounded. Uniformly bounded means simply bounded here. And so uniformly bounded is stronger than pointwise bounded. But in the presence of equicontinuous, that is saying, in the presence of equicontinuous, they are all same. That means if you start with S equicontinuous, then totally bounded, uniformly bounded, pointwise bounded will be all same. So here C, you are getting this thing. That S is pointwise bounded plus equicontinuous. Look here, I'm not bothering you about the proofs of that, but you should. B implies C is immediate because what uniformly bounded implies pointwise bounded. So it is this proof is immediate. Okay. Now A implies B. You should look how totally bounded. It is not difficult. In fact, it's a small technique. You should learn it. So A implies B. You should read. If you understand or not. If you do not understand, you can ask me. You can ask the tutorial teacher. A implies B. That you must do. Okay, that how it is coming. Look again, you will see that we are getting a finitely many things. Actually, S is equicontinuous if S is finite, but if it is infinite, that is the thing problem. If S is finite, it will be always equicontinuous. But if is a look, I am going for A implies B totally bounded. Obviously, it will be uniformly bounded means simply bounded, but I'll have to prove it is equicontinuous. So actually, this is the important thing. S is totally bounded. This is the thing. Implies S is equicontinuous. So where compactness will come? Because if it is compact, we have already seen in metric space that has to be totally bounded. Remember that a metric space is compact if and only if it is complete and totally bounded. So if it is compact, then obviously it will be totally bounded, it will be equicontinuous. Now the thing is, this is the thing you need to prove. A implies B, because totally bounded will imply boundedness. And look, by totally bounded, we will get hold of, we want to make S finite, we will get hold of a finite subset of S through which I will get this equicontinuous. Through which, so technique is here. Okay, so that you'll have to read. I'm not going to do it. Okay, and now C implies A. I'm just saying this is a bit tricky, but I am saying at least you read the proof. You see that whether you can understand. This you must do. Okay, so that in the presence of equicontinuous, three types of boundedness: total boundedness, uniform boundedness, which is the usual boundedness in CXD metric space, and pointwise boundedness. They're all same. And now look, I have given Ascoli-Argela theorem for as a corollary. Okay. Before remark 1.13, I am coming later on. So now look, Here, what is the connection with total boundedness compactness? Suppose you have, forget about that, XD I am taking in. Suppose this is a complete metric space. Okay, suppose you have Jan thing I'm coming, and suppose you have a subset of X. Let's take non-empty. Now look, if A is totally bounded, implies you can prove it from the definition. A bar is also totally bounded. Now, if it is complete metric space, closed, remember that closed subset of a complete metric space is complete. Okay, so that if you take this is complete, then close, this is a closed subset of this, so A bar is complete. That means with respect to this metric, actually, is complete. That means what you are getting? You are getting totally bounded as well as complete. But complete and totally bounded the same as is compact, so that it implies A bar B is compact. समझ गया? That means if you take totally bounded, implies A bar is compact. That means you are getting this case A bar is compact. Okay. Now on the other hand, if you have A bar is compact, so you are doing in a metric space, implies A bar is totally bounded. It is complete as well as totally bounded. But any subset of a totally bounded subset will be also totally bounded. Implies A is totally bounded. Actually, similar thing you used last year's minor question. You देखो last question I think not last before one before the last. A is totally bounded. We have seen if A is totally bounded, then A bar is compact. And here I am saying A bar is compact means A bar is totally bounded, any subset is totally bounded. That means what you are getting? That means you are getting A bar is compact if and only if A is okay. Look, just by using this, now you look. CXD is a complete metric space. Look, in a compact subset in a metric space, in a Hausdorff space, will have to be closed. So that's why for original Ascoli algebra theorem, if we go for compact subset, we'll have to add closedness. That exactly we did in this. Now look, I have given you the in terms of the total boundedness. I have characterized total bounded in terms of equicontinuity. So S is totally bounded. Look, this is a complete metric space, totally bounded if and only if S bar is compact. Okay. So that exactly the Ascoli compact let S be a non-empty subset of then S is compact in CXD if and only if S is closed and bounded in CX. Look here, Ascoli-Arjula, original Ascoli-Arjula theorem. This is the original Ascoli-Arjula theorem. Look, suppose X is a compact Hausdorff space. If you feel comfortable, you can take a metric space. Look, don't confuse X. I do not need metric space. CX will be a metric space. Okay, X is a compact Hausdorff space. Then CXT. Okay, X is a compact Hausdorff. This is your only hypothesis basically. And let S is non-empty subset of CX. Then look, following are equivalent. S is compact. Don't confuse with the same S. Here I am taking basically S is my S bar because I am taking closed. Okay, and B obviously it has to be closed and bounded in any compact subset in a metric space is closed and bounded in CXT that I have written specifically. And for equicontinuous, I do not need this thing. Equicontinuous can be defined. Okay, as long as you have real valued continuous function. And S is equicontinuous. Look, this bounded, it means be careful again. Recall, this is same as what we said, uniformly bounded. Okay. Uniformly bounded. So that exactly I promised you that closed and bounded subset need not be compact. Here in this case, the gap is equicontinuous. That means what you are doing, if you are taking this thing, look here I can give this metric because this I have taken compact Hausdorff space. Look, whole thing cannot be here compact CXD. Compact only for the subsets you are looking for that. You can think of that. Why the whole thing cannot be compact unless X is finite. Okay. If X is infinite, then CXT itself, you think about it. That if you can't do it, it's fine, but there is no harm in thinking. It's never compact. Okay, so that actually depends on the dimension of that. Cx is a linear space. So if X is infinite, then Cx will be infinite dimensional. So it's a compact Hausdorff space. And then if take this, then look, what is A? S is compact. Putting the following condition that before the S is compact. I'm taking a subset in CXT and B, what I'm saying, S is closed, bounded in CXD of course, and plus equicontinuous. So every compact subset will be closed and bounded, but only closed and bounded won't be equicontinuous. Only won't be compact. So the gap is this equicontinuous. If you put equicontinuous, then it will be compact. Look, I have already proved totally bounded will have to be equicontinuous. I have not proved, I have asked, given you exercise. A implies B in the previous result. Okay, so by that it will be equicontinuous. But now if you have equicontinuous, then it will be compact. So this is the gap. So this is, look, Heinbudel theorem for Rn is if it is compact, it will be closed and bounded. Here we are getting on CXT that it will be compact if and only with closed bounded and equicontinuous. So this is Heinboden analog. Similar thing, analog for CXT. समझ गया? Well, and what I said in the remark that X compact is बहुत जरूरत है, important. If X is not compact, then Ascoli-Arjula theorem need not hold. Okay, that look here you should, this is a bit computational, but it is very straightforward. You take X equal to R with usual distance metric. This is not compact, sorry. This is no, so not compact. That means this space, not compact. Now you take this thing. Basically, you take a sequence of functions. S is Fn, n belongs to n, okay, right? And if for each n you are defining Fn R to R. Here X is also R, this R to R, they are defining. Okay. You should check that S is equicontinuous. Pointwise bounded. I told you that. Pointwise bounded need not be uniformly bounded. So this is not uniformly bounded. Actually, you can prove this equicontinuous pointwise bounded, but not, I have given you the not totally bounded. So since it is not totally bounded, okay, look, this is, but this is not uniformly bounded either, because if it is uniformly bounded, then plus equicontinuity will give you totally bounded. Okay, right? So that first of all, look that not totally bounded. No, sorry, I think you should check that whether it won't be uniformly bounded, because I am not taking X compact. Okay, forget about that. Not totally bounded. Look, I have given you this thing. Actually, it's a misprint. It will be big D. D, Fn, Fm. It's not small d, it should be big D. Yes. Big D. Fn, Fm is, that you should check. So obviously it cannot be totally bounded. Okay, right? Look, totally bounded matlab kya hoga? First of all, it has to be bounded. Okay, right? So it is not coming bounded. Okay, is it coming bounded? This is this. Sorry, 1 minus e. That's what I'm saying. This is not 10. That means if you choose epsilon less than this, then obviously you won't get this. For this epsilon, total definition of total boundedness won't work. Understand? Okay. So that this is not totally bounded. Check if it is uniformly bounded. Check. Exercise. If S is uniformly look here, I am getting there bigger than this, but still I can have some bigger M than that. Whether that works on that. That to check. This is the question. It is not totally bounded, because if you take epsilon less than this, it won't work. Okay. So that you should check. Okay, so this X is compact. This is very vital in Ascoli-Arjula theorem. Okay, so that Ascoli-Arjula theorem, in fact, in PD often look how they apply. They take in, suppose, look here I am telling one application that at the end of the his proof, that proof and Aliprant's Barkin's kitab, they have mentioned it. Suppose X is a compact metric space. Take. Particularly, you see that with closed interval, closed bounded interval, this is compact. So if you take function, real valued function defined on this, then you can apply Escalade-Jellach theorem. So X is a compact metric space. Okay. And you see that. X is a compact matrix, suppose. So you are considering this thing, Cx, D. Now suppose, like this example I was doing, though it is for counter example, suppose S is a sequence of functions. Okay, in the Cx. Now suppose this is equicontinuous. Oh, here I have given you that exercise. If any set, if for X, if S is equicontinuous, then you can prove that implies S bar is also equicontinuous. Like if S bar S is bounded, S bar is bounded. If S is totally bounded, S bar is totally bounded. That should follow because they are very close. So this is also true. This you should prove. Okay. Okay. Now look. So that S bar is coming. Look, is closed equicontinuous. Okay. I do not know it is uniformly bounded. That I need. Uniformly bounded means bounded. Suppose S is bounded there, uniformly bounded. Suppose S is uniformly bounded also. You assume equicontinuous plus uniformly bounded. Okay. Actually, it is in general true what I am proving on that. Usually, PDE people use that. So, equicontinuous plus uniformly bounded. Basically, uniformly bounded, again, I tell you, that means bounded here. That means you take a bounded sequence here. Bounded equicontinuous sequence here. Bounded equicontinuous sequence. Then this will be closed, equicontinuous, and closure of a bounded C is also bounded and bounded, uniformly bounded. Okay, so that by Escalade-Jellach theorem, it will be S bar is compact. Okay. Now S bar is compact. Now look, S is actually sequence. But in a metric space, we have got sequential characterization of compact subset. If every sequence has a convergent subsequence, right? It is itself a sequence. This is compact set. So that it will have a convergent subsequence. But be careful. That will converge to a point in S bar. So limit may not be there. So that you get by the characterization, sequential characterization of compactness in a metric space. This sequence S Fn has a convergent subsequence. But that limit may not be in S, it will be S bar as a convergent subsequence. But that will be good enough. That exactly they use as a convergent subsequence. That means what I am getting. If you have a bounded equicontinuous sequence, here it will have a convergent subsequence. Okay, but convergent, the limit may not be here. Limit maybe will be in S bar. Okay, that is the thing they use. Okay, here lest I forget, I should tell you that one thing. I don't know whether that exercise I have given about the exam importance of metric space, the compactness. Sorry, look here in R square you have got this. Look here, to take a graph, this thing in R square, and if you take this is B. Look here, DAB is 0, though A intersection B is empty. Okay, right? Got it? Now suppose in the metric space, I'm giving you Inyan. A is closed, B is compact. Here none of them is compact, because none of them is bounded. Okay, by Heinberg theorem, none of them is compact. Suppose B is compact, that means one of them is compact and A intersection B is disjoint. Here I am giving one of them. Is it true? Then DAB has to be greater than or equal to 0. Okay, but you will have to use the compactness of this. Look here, you should understand the function. If you take this function or this function, there are continuous functions. Okay, but when you have compact, look here, the bound will be attained. That means particularly infimum and supremum. This is infimum. Think about it. Okay, be careful about it. This is very important. If B is compact, then it will be greater than 0. Okay, right? Fine. So that Ascoli-Arjula theorem basically more or less I completed, but I'm saying B implies C implies A, you should read the proof, but A implies B, you should do the proof. And this thing you should not forget, that I'm giving you this thing, that Cx, X is a topological space. To take, you can house drop, you can take. S is a subset of Cx. This is non-empty. Show that. So S is equicontinuous, which I have used. This follows from the definition, implies S bar is also equicontinuous. Well, I'm just telling you, if you need it to be compact, you can assume it, but you won't need it. If you think, in fact, if you first you can do this compact metric space. For that, you prove it. Anyway, we have used that. If you feel comfortable, you can take that. X is a compact metric space. Prove that S is equicontinuous implies S bar is also equicontinuous. Okay, right? So make sure that you understand the statement of Ascoli-Arjula theorem. Okay, Ascoli-Arjula theorem, it is not only in this course, you will need almost everywhere. Even applied mathematics in, you will understand. Okay, next thing I want to talk about Stone-Weierstrass approximation. I'm not going to give you any proof of that. Look, that Stone-Weierstrass, there are two people. Weierstrass did it for a special case, space in the real line, stone. Look here, I said some Many. Okay. What I want to tell you that in math there are two stones, H stone and MH stone. You go to the net, you figure out which stone is this one. Okay, both of them are famous actually. Okay, so that Stone-Weierstrass theorem. Okay, right? Stone-Weierstrass theorem. So which stone it is? H stone or MH stone? And one of them is British, one of them was American. And one of them actually died in 1989, I think, at a very old age, but he died in India. He was traveling in India that time. Okay, so that you should figure out. Okay, but now I am interested. What is the importance of Stone-Weierstrass theorem? I'm not going to give you the proof anything. I just want to explain that. Okay, that why people are this thing. Look, if you have a metric space, it may be very big, but suppose you have a dense subset, particularly suppose A is countable, countably infinite. Like, look here, often we simplify the properties of R in terms of the Q. Q is because Q is dense in R, and Q is a small set, countable set. So that in YAL, if you have a topological space, so that look, X itself is dense in X, so that's not a big issue. But suppose you have D, the subset of X, don't confuse with the previous metric D, it is a subset. Suppose D bar X, and suppose D is a nice set. Nice set means that is very subjective. It essentially means this you can handle. That means many things about D you know. Nice things means if you have the facts, if you know somebody well, that's in that sense is nice. If you have something unknown, you do not know much about somebody at that, then you do not know that, you do not know how to deal with that person. But if you know somebody well, okay, you can deal with that person better. So nice set in a mess means you have more information. On D, and also D has some nice properties, more information, and D has some nice, like Q, D has some nice properties. I am talking about the philosophy behind this theorem, so that if you have this, even general topological space through net is a generalization of sequence, you can have it. But take the metric space, if you have it, if you have this, then many things of the metric space you can do through this. That's why we are often interested in some nice dense subsets. Now look, here I said in this section we prove the Stone-Weierstrass approximation. Approximation. Be careful about approximation. Okay. Before I prove this theorem, I would like to mention that strategy that I said our proof is a combination of those employed in Aliprantis-Barkin saw, because Aliprantis-Barkin saw एक proof में गलत है. That's why we had to avoid that entire thing. And two, that is okay. Here, what I'm saying, H stone, MH stone. In the references, you will see this is MH stone. Okay. Applications of the theory of Boolean rings in general topology. MS transaction. That's a big journal on that. Okay, right? And since it is published in the MS transaction, he is the American. The H stone is the British. Well, about H stone, MH stone, one mathematician once joked, because actually MH stone is his name is Marshall H stone. And one Somebody joked that one is marshal, other one is field marshal. Okay, right. So that here you have combined the proof on that to give an easier proof of this. Okay, now that I told about the strategy in that. Okay, and here also I mentioned that first proof in 1937 by M.H. Stone. First proof in 1937. Actually, the approximation theorem gives a family of nice dense subsets of CXD, where X is a compact house of space and D is the supremum metric on CX, defined by DFG. Okay. In order to prove this, okay, I will come back on that. You are doing linear algebra. Okay. I don't know whether you have done it. You are doing it on algebra also. Okay, let me take about, because we are talking about algebra function. So you see, you have done here in ring, and here you have did linear space. That is a vector space. समझ गया? Vector space, here you have additions and scalar multiplication. That means you have something vector v plus w and alpha v. Alpha is a scalar. You took the scalar field. Okay, and here ring, look. What is the difference between vector space and ring? You had that because of the additive group, you have the addition. Addition you have. So here you have addition and it is scalar multiplication. I am telling you something more because that you need better understanding of the scalar multiplication. Here you do not have scalar multiplication. You have two elements, x, y, then x plus y and xy. That is multiplication. Multiplication of the elements. Here no outside this f is involved. Okay, right? Got it? Now suppose you can some structure you have where you have both, that is a linear space as well as a ring. Okay, that's not unusual. Look at this. If you take even this, CR, that means all real valued continuous functions on R. Now look here, you know sum of two continuous function is continuous. Sum is defined. You know scalar multiplication of a continuous function is continuous. You know product of two continuous function is continuous. Product. Three operations are here. Okay, three operations are here. Here with these two operations, this is a linear space, vector space. Whereas if you take these two, a plus g, that gives you ring. So actually you're getting three operations. Not only that, look, this basic philosophy nobody else will teach you. Let me tell you that one thing. That's a basic philosophy. When something, if you take x8 and you are going to have more than one structure, that is more than one operation, you can say that. Then these operations will have to be compatible. Natural, I am going to explain. Operations will have to be compatible, naturally compatible. What do you mean? Look, I am coming to that. If they are not compatible, what is the briefly, loosely you think that there must have some relations, natural relation. If you don't have any natural relation, then I won't study at the same time. I will study them separately. Like you did in B.sc in ring. Look, ring, you had the group structure. Okay, you are taking this. Don't confuse with this. This is real line and two have to go. Suppose you have ring. and this product. So you have, this is the abelian group. This product is associated. These two are different operation, but where I made the natural link, this is distributive property. Look, two operations, they are not independent. They are linked by this. They are joined by this. They are bound by this. That's a natural thing. Here I am taking addition and then I am taking multiplication. Here I am taking addition the other side. So distributive property is the compatibility. I was talking about compatibility. Look, if I didn't have this, then I won't study them together. I will study these things separately as a group and separately at whatever I can do that. I won't study them together. That's why you have it and then we study it together, and then that means we study rings. Okay, we study rings. Similarly, if you have the vector space, look, if you have a vector space, this is the addition. This is just a notation, juxtaposition. This is scalar multiplication. But again, you have two operations. Okay, but we are not studying independently. There must be a link, natural link. If you don't have it, I will study them separately. Why I will study them at the same time, simultaneously? And how that was given by that? That was given by the last four properties. Look here, you had this alpha x plus y. These are vector, this is scalar, equal to alpha x plus alpha y. Okay, right? And some other things on there. I don't know what else that. Okay, like here one thing is there, that is scalar multiplication, that you can take this. This is only scalar multiplication, but still you need compatibility. That this is this. Since it is filled, you are taking, this will be this. And 1x is same as that. X, 1 is the unit of this. And another one was there. What is that one? This one. Alpha plus beta x vector. Look, these two gives you the connection between scalar multiplication and addition, vector addition. And these two are other natural conditions required. Okay, but these are the compatibility. This I am talking about compatibility. So that means unless you have compatibility, you don't study them together. Now suppose I'm just doing something else. Now suppose you have a structure, three things. I'm just writing this notation. This is addition over a field. Suppose this is scalar multiplication. This is multiplication. What does it mean? That means here you have this x plus y addition. Here you have alpha x. Alpha is a field, the scalar field over that, scalar element. And here you have xy. Okay, right? Suppose you have this. Okay, now suppose first of all with this operation, this is a vector space. And suppose these two with a ring. Okay. But here I have got three operations. These two, since the vector space, I know they are compatible. These I'm saying these two are compatible. But what about all the others? That means I have not talked about this. Scalar multiplication and multiplication compatibility. This compatibility. They help it to compatible. And you should figure out that what it should compatibility means. Should. Okay. One thing you can see easily what will have this. This if you have it, I should have. Right? Okay. So that you should see the natural compatibility. Suppose you have that natural compatibility. You have three operations, all these. These two the vector space with this ring and like this. And you can think of that whether other things also you need. Okay, right. Then this is called an algebra. If you are reading Huffman and Kunje from the linear algebra, I don't know which book teacher is following. That there cannot be any better book than Huffman and Kunje. That linear algebra. There they have talked about algebra also. Okay. Right? Huffman and Kunje theorems are important on that, but thing is that this book has too many important examples and too many important comments. Sometimes comments going for more than a page. Okay, right? If you have done already some linear algebra, make sure that you understand minimal polynomial. Well, whether it depends on a field. Well, I will come to that point. So this is called algebra. Why I'm talking about minimal polynomial. Suppose you take a matrix M over R. I'm just giving you this question. But this can be also considered a matrix over C also. So is my question the minimal polynomial of course you take a square matrix. Minimal polynomial of M over R is same as the minimal polynomial of M over C. This is a very simple question, but I'm pretty much sure your teacher didn't teach you. Huffman and Kunje around
No,
page. Hello? You know it?
these are not these are notes.
Huh? Will be same or
Same
not?
notes.
It will be same. I am telling you the result. It will be same. And if you want the proof, you read Huffman and Kunje, I think around page 100 something. And he was using a theorem in the very beginning. That's why I'm telling you, he was making a comment. This is same. In fact, minimal polynomial over in YAL, if you do it field, suppose you have this is a bigger field. Minimal polynomial will be over this will be same as this. If you start with a matrix over this. Okay. In fact, one student, he did M.sc here. In the PhD interview, he was saying he wants to answer questions of linear algebra. तो मैंने उनको पूछा तुमने कौन सा किताब पढ़ा? वो बोला मैं हफमैन एंड कुंजे पढ़ा. I was like, you know Huffman and Kunje well? He said, yes, I know well. मैंने उसको सीधा ये क्वेश्चन पूछा. And I think the first time we heard this question. This question is very standard. I am telling in a sense, if you go for somewhere interview and that, very likely if somebody likes an algebra, you will ask you this question. Okay. And मैंने उनको पूछा. Then he was lost and finally said, no, I do not think they need to be same. And then it means that you have not read Huffman and Kunje properly. Well, Go back and see that where you can find where Huffman and Kunje started introduced minimal polynomial in that same page before giving any theorem he was talking about. Okay, but look about what about characteristic polynomial? Characteristic polynomial, you do not have this problem. You can see that this question do not arise. Okay, because characteristic polynomial is defined completely different way, because minimal polynomial is defined basically it's an ideal, it's generator. That generator is called the minimal polynomial, the unique generator monomial with coefficient 1, leading coefficient, that. So right, okay, fine, that you should read it. Now look why I'm doing it in CX. In fact, if you take fx, fx is the take the set of all real valued function. X is a non-empty set. Now I can define, look, f plus g pointwise addition, fx plus gx. Real valued also take scalar field, you will take r, like alpha fx you define. This you are defining. This is mean alpha fx and fg x fx. With these three operations, fx, look, algebra, first of all, you need vector space, so it has to over a field. Here, fx is an algebra over R. If I took complex valued function, it would have been an algebra over C. Understand? Now you could take any field depending on the vector space. I am doing the simple case. Okay. Similarly, now if X is a topological space, X tau, then Cx. This is an algebra. Because sum of two continuous functions is a continuous function. Scalar multiplication of a continuous function. Product of two continuous functions is an algebra of functions. This we call it algebra of functions. Okay. So Stone-Weierstrass theorem, I have taken so much time to explain this algebra. Okay, right? So that here a collection L of real valued function defined on a set X is said to separate that. Okay, vector space, the V of real valued function on a set X is called an algebra of functions whenever the product of any two functions in V is again in V. Already we are saying it is a vector space. So that's why I need to talk about, I'm doing special case of algebra here, functions. So I need to ensure the product is also there. Look at just the definition before lemma 2.1. 2.1. Okay, so the algebra of functions. Okay, now suppose you have this function defined on a set X. Suppose fx as a function. An L is a collection of that subset, and we say that it separates points of X. This is in topology from analytical viewpoint is very important. Next semester I will tell you more. Separate points of X means that whenever you take 2 points, suppose in X, so there exists f belongs to L such that fx not equal to fy. That is called the separate points of X. The separating. Okay, that is the thing. That fx not equal to fy. We have taken phi such that phi a not equal to phi b. Okay. I'm not going to this. I'm just going to introduce on that. I think next semester, if I get time, I will give you the proof of this Stone-Weierstrass theorem, which I proved. Okay. Now, thing is that lemma is there. Lemma is required. Lemma is currently in a short thing and that, but it is very interesting. Now, what is Stone-Weierstrass theorem? Theorem 2.2 is telling. I'm just explaining, and you should read the proof either before the exam or after the exam. You should see that. Okay, right? But what is theorem? That it will be enough right now to know this statement. Suppose X is a compact Hausdorff space. Hausdorff space. That means the CXD is a metric space because I'm taking compact. I'm looking for nice dense subsets here. That exactly same. Let A be an algebra of functions. Algebras of this real world function x separating the points of x which constraints. Okay. Real world continuous function. That means first of all this. Everything I am working with continuous function. Look, A be an algebra of real valued continuous function on x separating points of x. Separates points of x. Separates points of x. Not also that one constant function 1 belongs to. We'll say why it is important because we are going to apply lemma. Okay, then A is dense in x, NCX with respect to this metric. Then A is with uniform metric that I told. Look, hypothesis is not one. This is compact you need because you want to ensure this is a metric space. And A is an algebra. That's why I took so much time to explain algebra. And it has the constant function 1. Okay, right? Look, 1 is there. It is a vector space. But algebra, you are saying, look, algebra, I am saying vector subspace and that. Okay, right? So it will be leak always this. But I am saying for all A belongs to this also. Be careful. Here I am saying 1 itself belongs to A. If you have this, then A is dense in this. Actually, why Stone-Weierstrass comes? Because this result is Stone's result, very general, and Weierstrass result, which is now corollary. Look, that is corollary 2.3. Look here. Actually, Weierstrass did for only closed interval 0, 1. But if you have the real world function in a compact subset A of R, so you taking R, and suppose A is a compact subset. But compact subset, you know, it has to be closed and bounded. Compact subset of R. Okay. Then any continuous function and a compact subset A of R, that means if you take any function, continuous function, it is saying it is a uniform limit. That means with respect to D, sequence of polynomial functions. Here I am saying polynomial functions. Here I should tell you something. We are doing algebra, you should know. There is a difference between polynomial and polynomial function. Polynomial function means it's a function which has the form of a polynomial. But polynomial, be careful. If it can be defined over any ring. Look, R to R. This is sort of like this. Look, here it means look here, if plug X, you get this. It's a polynomial function. But look, I don't know who is teaching me algebra. Ritumani, who else? Who is teaching?
Yes, sir. Ritumani, sir.
Ah, Think about this polynomial. What is this x means? What this x means? You are doing polynomial over a ring that usually defined as a sequence like this.
Yes, sir. Except finitely many baki that's all are
X
zero.
क्या है? What is
Uh,
x? X is not defined there as a polynomial.
yes, sir. X is not defined. X is coordinate function.
What is coordinate function? Polynomial तो ये हो गया. What is x?
Yes, sir.
Ask yourself. Think about it. What is x?
Yes, sir.
What is x?
पॉलिनोमियल फंक्शन पे वो unknown है।
नहीं. Look, in order to
पॉलिनोमियल
define
फंक्शन
x, first of all, let's see why. In order to define x, R must have one identity. If you don't have it, okay. Actually, यहाँ पे इसके बाद I am wrong because it can. This is comes like okay, and these are all sequences. These are such a sequence is a polynomial, and if you have one, then this is this. This is actually x. Polynomial over R ring is nothing but a sequence where you have only finitely many non-zero entries. Finitely many non-zero entries. If you insist of infinitely many non-zero entries, then power series comes. Okay, that is called in algebra formal power series. Formal power series. So unless you have one, look, this one is important. Your x is not there. But that's why I'm saying I don't need it. But polynomial function is this. Here x is a so-called variable. Here it makes sense. But here no such x is there unless you have this. Understand? Only when you have x this, then any polynomial of this form can be written like this. Because then the product of two polynomials is also defined. X to the power n means a, you multiply itself with itself n times. समझ गया? Then it makes sense. Otherwise, it doesn't make sense. Okay, right? Here,
Yes, sir.
another thing that you should read on that. Another question I'm leaving it to you. When you go for interview somewhere, they will ask you this thing, and you first of all you will feel lost, and then you'll see ये तो कभी किसी ने पढ़ाया नहीं. As if I have you, then you think you are hearing that question for the first time. Okay. Another thing, here I know that if I x sum a is here, I can get fa. Okay. But when you have a polynomial over R, P, often we write Px and then you take a substitute Pa. What is the meaning of this? There, even if you take R with 1, then Px sign is the polynomial. Okay. Then you can write like this. But what is this? So I am substituting a. So, but ये तो polynomial है, ये क्या है? What is this? When you are doing algebra, you have a polynomial function, it's fine. That's why I'm emphasizing. There is a big difference between polynomial and polynomial function. Polynomial function means it's a function of that form, the polynomial form, nothing else. It's a function. But ये PA क्या है? PA is defined, but how it is defined? Huh? Just think about it. Anyway, if you are interested in algebra and that, if you want a good book, this is Thomas Hungerford. Indian edition is available. It is originally Springer Verlag books. Thomas Hungerford. Hungerford. Name of the book is Algebra. You can read. Okay. You can see that. All these questions you'll find answered there. Okay. And of course, that I think you have read here, but you didn't know that who was behind that Indian edition and that. I think in undergraduate you have read his algebra book, I think. Many of you, Galilean Algebra, Joseph Galilean. This book, Indian edition, is available. Actually, I was behind the Indian edition. I got it published. This is for undergraduate, it's a good book. But if you want to go beyond undergraduate, you want to know something algebra, then you should read this book. So I'm just mentioning in this polynomial function and polynomial, they are different things. Okay. Now look here what I am using now. Okay. So that here the collection of all polynomial functions, if you take this thing, here you have this R, and take the collection of all polynomial functions. Call it the collection of all polynomial functions on A. A is the domain. A is the domain. A is a compact subset. Sorry. Here you're taking polynomial functions are continuous anyway. The collection all polynomial functions. Look, this is an algebra. This is not a problem. Okay. Only thing the one also is there. Only thing you'll have to check this is so this is algebra that you can easily check because sum of two polynomial function is a polynomial function. Scalar multiplication of a polynomial is a polynomial function. Product of two polynomial function is a polynomial function. One is a constant polynomial. Okay, so it is algebra. And of course, it separates the points because if you have 2 points, if here I have taken this, actually it will be, I'll be take, it should be, and if you have 2 points in A, then what will be the polynomial function you will be taking? Okay, right? A not equal to B. I can take simply this function. Okay, look, PA equal to A minus B and PB equal to 0. But it, and since A minus B not equal to 0 because A not equal to B. Okay, so it separates points. So it satisfies hypothesis of Stone-Weierstrass theorem. So it is dense by Stone-Weierstrass theorem. Actually, Weierstrass did A equal to he did on this. Now, if it is dense, but dense means what? Now look, A you have got dense. Okay, of all the continuous functions on that. So A you are doing on this. A is a compact subset of compact. And suppose this PA is density CA. That you are getting dense. But that means what? If you take any function here that is in closure, but in a metric space you have every closure point has a sequential characterization. Implies there exists a sequence Fn in PA such that Fn goes to F with respect to which metric? D. Right? That means D Fn. Actually, I have taken a better notation will be Pn. Sorry. Pn. Polynomial. That means what you are getting? That means you give me any epsilon, doesn't matter what small, I will get a polynomial such that TPNF will be less than epsilon, which means what? Soup of, I will get, there exists, actually there exists n naught such that TPN for all n greater than equal to n naught. Particularly for you will get dp n naught f less than epsilon. But that means what? No. X belongs to A. That means what you are getting? You are getting, look, it means you are getting Pn naught x minus fx less than epsilon for all x belongs to. That is, continuous functions behave very well on a compact subset A. That means you can approximate with a polynomial. Polynomial functions are much easier to handle. So that is called the approximation theorem, that you can here function, you could approximate through functions of A, not that A, that algebra A. Don't confuse with that subset A. Okay, that algebra. Here, particular case on the real line, you can, if A is compact subset of this, you can, any polynomial can, any function, continuous function can be approximated by polynomial. Approximation means this. That is why I called it Stone-Weierstrass approximation theorem. Particularly Stone-Weierstrass did for this interval. This is by Einmodel theorem closed and bounded. Okay, so that Einmodel theorem, it is compact. So particularly if you take any continuous function on a closed and bounded interval, that can be approximated by a polynomial. That's the result. Okay, so it for Ascoli-Arjala theorem, make sure A implies B of theorem 1.2. Read the proof. And Stone-Weierstrass theorem, it will be good enough if you understand the statement of theorem 2.2 and corollary 2.3. So what I am saying, make sure you understand the statement. Right now, you don't need to go for the proof of that. But proof of the corollary 2.3 already I explained. Only this proof you should read whenever you find some time, before exam or after exam, because next semester I will teach you this proof. Okay, right? So that I will take the class. I will tell you that either November 8 or November 9. I am telling you that I will send in. The only thing I have left in the previous note, I have Dini's theorem. It says under special circumstances, pointwise convergence implies uniform convergence. And I have a small note on connectedness that I have uploaded. Basically, I think in one lecture I can finish. I will teach connectedness. I will teach Dini's theorem. Okay. So I think I will take the class November 8. Okay. So let me tell you that for my question. Uniform convergence, you should equicontinuity. I may not give a question. Last year I gave a question. Even if I give a question, it will be a simple question. But uniform convergence, you should read carefully, because I may give you 2 questions on that. Okay. Particularly, I'm taking time, but I'm going to tell you before the break and that. Here, this 2 of you sent me the answer. Look here, that Fn 0, 1 to R Fn x equal to x to the power n. I gave the question that if it will be a subset of this, it will be uniformly convergent to 0 function if and only if 1 is not a closure point of that. I think you can prove this thing. Relate. Of course, if 1 is not uniform, 0, 1. Okay. Then following are equivalent. Let me tell you that what. That Fn converges to 0 function uniformly. This is the constant 0 function. Uniformly on A, B, 1 does not belong to A bar, and C, there exists B with 0 less than B less than 1. Okay. You can assume that. A not equal to 0. That is not finite. In fact, you can take A infinite. Let me tell you. Wait a minute. Because finite you do not know. Finite it will be always uniformly convergent. Infinite, the following are equivalent. There exists B with this such that is contained in this 0B interval. Look, on this interval, the function Fn is always convergent, uniformly convergent. B is strictly less than 1. I think this, I gave you equivalence of A and B. I am added this condition, C. But the way two of you gave me the proof, this is immediate, this comes this. So you should prove it this. Okay. So I am telling you that uniform convergence, you should read it. Okay. Equicontinuous, if you feel comfortable, at least you should know the definition. If I give a question, that will be a simple question. Just by using the definition of equicontinuity, you should be able to prove it. Okay. Right. But here, I am just leaving it to think about. ये तो थोड़ा behavior ठीक नहीं है, but do you think you can have a function defined? Okay, 0, 1, 2R. Is it possible? You define a continuous function such that Gfn converges to 0 uniformly on this. Fn, so you know that. What is the problem you are getting? But suppose, does there exist a function? I am asking the question, continuous function, such that Gfn converges to 0 uniformly on this. Okay. So next week I will take the class. Okay. So, but make sure that you read compactness. I am telling you compactness. Okay. Let me tell you that compactness you should read uniform convergence. Connectedness. I will give a question. Last year I gave a question that was a wrong question. That's why everybody got that marks. I gave them. But you should think about how to correct this. But this time I won't make that mistake. Actually, I just forgot to mention that extra is connected. Okay. This and this one I'll give you because otherwise you'll have problem. You'll have too many questions on compactness. This isometry. There is a note I have given that you should read isometry. Okay. And equicontinuity, I told you, just it will be enough. You know the definition of equicontinuity, you know the definition of equicontinuity and statement of Ascoli-Arjela theorem. Okay. But even if you want to don't take it, but make sure at least these 4 you read carefully, particularly uniform convergence. Okay. So see you on 8th. Okay. Okay. Bye. I'm sorry that I have taken so much time non-stop and that I had to do it because I wanted to finish it. Though Dini's theorem is due. Okay. Have a happy Diwali. Okay, bye.
Thank you, sir. Same to you.
Happy
Thank you,
Diwali,
sir.
sir.
Same to you, sir.
Happy Diwali, sir.